Hello and welcome to Parraid's How-To series of tutorials. Today we will be focusing on PCM special functions and embedded streams. In this tutorial, it is assumed that you are already familiar with how to set up sources and basic PCM streams. If not, please consult the manual, watch our How-To series of tutorials, or contact us for training. Contact information will be displayed at the end of this presentation.
It is possible that within an existing PCM stream, another PCM stream is embedded. If a PCM stream has a word map like this, where we describe rows as words and columns as frames, we could insert into some of these words the data for another PCM stream. That could be a block of data in the map, a column of data, or a row. It could even be supercommutated or subcommutated within the map. There could even be identifiers that indicate whether or not the embedded data is present at all. In this presentation, we will cover all the types of embedded PCM streams supported by Omega Next. We will begin with showing how to create an embedded PCM stream in Omega Next. An embedded stream is a second PCM stream that is inserted into a primary stream. These are sometimes called asynchronous streams. For clarity, we will refer to the primary stream as the parent stream and we will refer to the embedded stream as the child stream. In Omega Next, you can have multiple embedded streams and even embedded streams inside of embedded streams. We could call those grandchild streams. Here we start with our parent PCM stream, which has already been defined. The word maps show that we have 101 words per minor frame. This includes the frame sync and 20 minor frames. The common word length for this data is 16 bits per word. Embedded streams should be thought of as sources for data. As a source, it will still be necessary to create a stream for each embedded source. We will get to that later, but the first thing to do is to scroll down to the embedded streams section in the PCM section. The first thing we will do is create a new source by clicking the Add Source button. The first step is to give your source a name. We will call this stream No Filter. Of course, you can name it anything you like. Next, we will pick a color for this source. This is important, and choosing a good contrasting color will make it easier to identify which words are containing the asynchronous data within the word map. This will be very helpful to make sure you are choosing the correct words. Finally, we set the filter type. There are 4 choices for filters, and we will cover what each of them are and how they work. The first type, which we call No Filter, means that the embedded data is always present in the words that contain them. So, we will start with this filter and click Save to begin our setup. The next step is to assign locations for the embedded data. Locations are just words that contain the data. They can be anywhere in the word map, like a block, or all the frames in a word or group of words, or a group of words in a frame, or some increment of words or frames. They really can be located anywhere. So, how do we set that up? First, click the Add Location button. Note that you have choices for initial frame, initial word, frame and word increments, MSB, LSB, and number of words and frames. Let us start with something simple. Suppose our embedded data starts in word 25 and on frame 10, but it is only 4 frames deep and extends to word 40. The first thing we do is click on the Add Location button. In the initial frame column, we put 10. In the initial word column, we put 25. That gives us our starting point for the embedded stream. Now, we want the data to continue in both the frames and the words, so the frame and word increments will be set to 1. However, we want to limit the frames and words, so in the number of frames column, we put 4 to limit the number of frames used to 4. In the number of words column, we put 16. This is because we want the words to stop at 40. So, from word 25 to word 40, that is 16 words. You can calculate this by taking the word you want to end on and subtracting the word you start with, then add 1. So, 40 minus 25 is 15, plus 1 is 16. We are done. We have successfully created a source for embedded data. If there were more locations, they could be added as well, but for this example there is only 1. You can see the words used for the embedded stream in the word map of the parent. Now, you have a source for data, but you do not have a stream to see it. So, go to the Streams tab in Omega Next. You will need to click the Add Stream button and add a new PCM stream. We will call this stream No Filter. We will click the Source Channel button and select the No Filter in Parent Source. This is the embedded source. Now, you will need to set up this new PCM stream according to the frame geometry for that stream. The frame geometry, common word length, number of minors per major, words and bits per minor, etc. are completely independent of the parent stream. Remember that no filter means the embedded data is always present, but often the embedded data is only available some of the time. One simple way to indicate the absence of embedded data is a stale bit. By identifying a bit, then determining if that bit is at a particular value, either 1 or 0, for a second time, we can call that a stale bit, and this can be a flag that indicates the data is no longer valid. To set this up, go back to your parent stream, then go to the embedded stream section. We will add a new source and call it stale bit. In the filter type section, we will choose stale data bit. To set this up, you must choose which bit is the identifier. Remember, this is data within the embedded stream. The first bit of the first data word is considered bit 1, and then you must count from there. So, in our example, the common word length of this embedded stream is 8 bits, and the first bit of the second data word is the identifier. So, the first bit of the second word is bit 9. Omega Next uses the IRIG 106 standard for bit numbering. The most significant bit is always bit 1. Now, we need to set the value to compare for stale bits. In this case, it is 0. So, when bit 9 is equal to 0 and the data word is stale, the embedded data will not be processed. Now, we need to add a location for this embedded stream. In this case, the stream starts on initial frame 7 and initial word 73. The data continues through all the frames, but stops at word 97. So, we will put the value of 1, for both the frame increment and the word increment. We want the frames to continue to the end of the parent major frame, so we will leave the number of frames at 0. A 0 means it does not stop. However, we do want the words to stop at 97. So, using the same formula as we did in the no filter example, 97 minus 73, plus 1 is 25. So, that will be the value we insert for number of words. Once the location setup is complete, you can see the locations used in the word map of the parent stream. Like the function of a stale bit, a fill pattern can be used to flag if an embedded stream is to be processed. In our example, we have 16-bit words and we have the fill pattern EB90, in hexadecimal, to indicate whether the data should be processed. This time we have a more complex situation for our data locations. We have two locations. The first one starts at frame 15 and word 13. The frame increment is 1, but limited to 4 frames. The word increment is 2, but stops at word 71. As we did in our first example, we will set the number of frames to 4. But the formula for the number of words has to change. In this case, we have to take our ending word, 71, and subtract our starting word, 13. This gives us 58, but we have to divide by 2 to account for the word increment. This gives us 29. Then, we add 1. Now 30 is the value for the number of words. This gives us our first location. The second location skips a frame, but otherwise is the same as the first location. So, the initial frame is 20, then initial word is 13. Since frame 20 is the last frame of the parent stream, we can set the frame increment to 0. The word increment is still 2. The number of frames is set to 0 since it is the end of the parent major frame. The number of words, in this case, matches the first location, 30. Having the word map showing the locations is very helpful to know you got it right. As in every case, you will need to create a PCM stream to map to this data. Finally, embedded streams can be built on mathematical conditions. This can be done on a syllable basis. Meaning, each location can have a different condition. Mathematical operators such as greater than, less than, greater than or equal to, less than or equal to, equals, and not equal to, can be used to determine the validity of any specific syllable. We will cover some examples of this and talk about selecting bits from words to process, rather than using entire words. First, let's say that we have 4 locations and they are defined as follows. Location 1 starts on initial frame 8, and word 3. The frame increment is 0, and the word increment is 1, but limited to 10 words. In addition, only the most significant 8 bits from the words in the parent are to be used for the embedded stream. In this case, we would leave 1 as the value for MSB, and set the LSB to 8. For location 2, we have the initial frame 8, and initial word 3. The frame increment is 0, and the word increment is 1. Again, the words are limited to 10. This time, we want to process the 8 least significant bits in the parent words. So, we set the MSB to 9, and the LSB is left at 16 bits. Location 3 has an initial frame at 11, and the initial word is 6. The frame increment is 0, and the word increment is 1. The words are limited to 10. This time, we want to process the 8 most significant bits in the parent words. So, we set the MSB to 1, and the LSB is left at 8 bits. Finally, location 4 has an initial frame at 13, and the initial word is 8. The frame increment is 0, and the word increment is 1. The words are limited to 10. This time, we want to process the 8 least significant bits in the parent words. So, we set the MSB to 9, and the LSB is left at 16 bits. Now, the locations are set up, but we still need to set up the conditionals and assign them to the locations. We start by clicking the Add Condition button. In the first column we have the name of the conditional, which is defaulted to Conditional 1. The name will auto-increment the number, but you can change the name to anything you like. In this case, we will call it Con1. Next, we give the location information for the word that contains the condition. For our first conditional, the initial frame is 8. The frame increment is 0, so the condition is only in frame 8. The column called DW number means data word number. In this case, it is data word 2. For conditionals, the DW number is in reference to the parent frame, and not the embedded stream. Next, we can set the DW mask to determine which bits to look at. For this conditional, we will set the mask to the hex value, F, meaning we will only look at the least significant nibble of data. Now, we will set the operator. Our choices are greater than, less than or equal to, greater than or equal to, and not equal to. In this case we will choose equal to. Now, we set the value to compare. For our data, it is 6. For the second conditional, which we will name Con2, the initial frame is 9, again with a frame increment of 0. The DW number is 3. For the mask we only want to look at the most significant nibble, so we will set the DW mask to F000. The operator will be less than or equal to. And the value to compare will be A in hexadecimal. Note that the DW mask and the value are both in hex. Our third conditional we will call Con3 is at the 11th frame, has a frame increment of 0. The DW word is 6. We want to mask for the last byte in the parent word, so we set it to 00FF. The operator will be not equal to, and the value will be 3D in hex. Finally, our last conditional is at frame 13, and word 7. We want to look at the whole word, so we will put F in the DW mask. The operator will be greater than, and the value is EB70. Now that all the conditionals are set up, we just need to assign them to the locations. To do this, simply go to the conditional column, click the pull-down box, and select the conditional that should apply to the location. For our example, we will assign Con1 to location 1, Con2 to location 2, and so forth. Any conditional can be assigned to any location. Now that all the embedded data has been identified in the parent stream, we need to set up another PCM stream to process this data. We will call this stream conditionals for clarity. However, you may choose any name you like.
Thank you for watching this how-to video on PCM embedded streams. Please watch more instructional videos by Parraid. If you are curious about Parraid, visit our website at www.parraid.com. For technical support, reach out to support@parraid.com. If you have more questions about Parraid products, please contact us at sales@parraid.com.